Hello, good morning, and here we are again for another exciting episode of CENG 3306, Mechanics of Materials. Alright, so today is lesson 19, and we are going to be studying in section 5.9, studying a variety of things, but in particular we're going to be looking at, for the learning objective for today, using the appropriate failure theory to design and analyze structural members made of brittle and/or ductile materials. In particular, we are going to be looking at torque. Again, taking torque a bit beyond what we've been looking at previously. So previously we've looked only at elastic torque, and now we're going to look at elastic and plastic torque. So let's do that. Bit of business for the students in this class this semester. The partial credit for exam 1 is now posted, and we do have exam number 2 coming up on Thursday. So on Thursday evening, we will have exam number 2 from 6 to 9 p.m., so please be available for that. All right, so as we have when looking at plastic materials before, we're going to use an elastic plastic assumption in our analysis today. Just like we did for tension and compression and things like that. And when we are working with torsion, we are also going to look at, we're also going to use an elastic plastic assumption. So let's look at this. Elastic plastic assumption. Hopefully by now this should look very familiar. And let's see. So I'm going to assume this kind of stress-strain behavior in terms of shear stress and shear strain. Maybe I don't necessarily like it like that. Let me just fix this. That looks terrible. Make it a little bit bigger so we can see what we're doing. Much better. All right, so on my x-axis, I'm going to have my angular strain gamma in radians. And on the y, I'm going to have shear stress, tau here. Then I'm going to assume behavior like so. Now, yes, in reality, we know that the stress-strain diagram for shear and for normal stress and strain is going to be much more complicated than this, but we are going to assume this kind of behavior here. This is our elastic plastic assumption, where we have simple linear elastic behavior and simple flat plastic behavior. In other words, here is our shear stress, our elastic shear stress, or our yield shear stress. So in reality, we know that yes, the material will actually behave something more like this, going parabolic, and then has humps in it, a hump at the end, and then it goes to rupture over here, etc., etc. But for our assumption, to make our analysis more possible, we are going to make this approximate but well-founded assumption here. And since at first it may seem, hey, how can you possibly assume this? This is obviously not true. But you have to remember that this is greatly exaggerated. In reality, to draw this properly, I would have to greatly stretch this out many times across the screen. This is not to scale when we draw it like this. So a flat or a constant stress for increasing strain is actually not a bad assumption for plastic behavior, or a bad approximation, perhaps I should say. And the slope of this line is not going to be the modulus of elasticity, but the modulus of rupture. Okay, so just as previously, we've had a relationship here. Let's see. Let's look at this. There are two equations that are going to govern this. We've seen previously the tau equals T rho over J. But we will also be governed by G equals tau yield over gamma y. So G again is just going to be tau yield over gamma y. Again, that's just more of a definitional relationship. And so this is just basically a review of what G is, or in terms of stress and strain for shear, and then a review of our formula for shear stress for torsion. Okay, and again, further review, what we mean by rho. We're going to analyze a certain distribution of stress and strain, but we're going to have a certain relationship that is in relation to the R and the rho. So again, R and rho are along this axis, where rho is where you are at any given point, and R is the actual outer radius of the member, and tau is your stress therein. Okay. But now, so we'll be using that as we go along. But a key to inelastic torsion, the key to inelastic or plastic torsion, is as follows. This relationship here is what will allow us to really fully analyze inelastic torsion. So this is our guiding relationship here. Gamma equals rho times phi over L. Gamma equals rho times phi over L. In other words, shear strain is linearly distributed about the cross-section. Shear strain is linearly distributed about the cross-section. So in other words here, for a given angle of twist and for a given length, these are, for a given system of torsion, these are going to be fixed. So in other words, as your radius, your distance from the center, not your actual radius of your object, but not your actual physical radius, but as the radius rho that we're looking at, the distance from the center of where we're looking for the strain about, it is directly, literally, linearly directly related to the radius, the shear strain is. So we can see that. So in other words, there is a direct relationship. So let us look at how this actually applies in terms of gamma distribution. So I'm going to draw a big old diagram and make some nice perfect circles. Gamma distribution. All right, so we know that gamma is going to be linearly related to the radius, or the distance from the center. Now I am going to draw, what I'm going to draw here is I have a object that is under a great deal of torsion load, and it is both has both elastic and plastic. It has I should just say it has three components. One, it has a hole in the middle. Two, it has an elastic core, and three, it has a torsional zone. Or sorry, three, it has an inelastic zone. All of it's under torsion. I just can't talk this morning. So gamma distribution. Well, maybe it'll make more sense if I just try to draw it instead of ranting about it. So let me draw a few perfect circles as normal, or something that looks more like a potato. So these are supposed to be perfectly circular, but the best laid plans of mice and men also often go awry, so there you have it. have this. This is along the vertical axis, I'm going to plot our gamma. And along the horizontal axis, I am going to plot our rho. Now, let me label each of these things. I'm going to put some colors on here. So to label these zones clearly, well, hopefully clearly, let me label a green region, a blue region, and perhaps an orange region, or maybe even a purple region, just for fun. Okay, so what are each of these things? Well, first of all, the cross section is the outer surface area. The cross section is in black. This is the cross section. In the green, I have a hole, just a hollow section in the middle. This is a hole. In the blue, I have the elastic core. And in the purple, I have a plastic annulus. In other words, we have an outer ring that is going to be in plastic stress, or under a plastic loading condition. We're going to have an inner ring that is going to be in under an elastic condition, and our inner core is just going to be completely hollow. But our actual strain is going to be linear throughout. So our strain just keeps on increasing right onto the outside, right up to the outer surface. Gamma max here. And it would go all the way to the zero. It would go all the way to zero if there wasn't a hole here, but there is a hole here, so this is actually the minimum value that we'll have for the strain. And this thing just keeps increasing linearly throughout. In other words, the strain does not care whether this is elastic or plastic. The stress definitely does, but the strain does not. The strain simply happens as if the material will behave linearly however it wishes to. And this here, right at the boundary between the elastic and the plastic zones, is going to be gamma y. This is gamma y, the yield strain. In other words, the relationships we can have here is gamma y over rho y equals gamma max over CO. And let me define these. Let me define those 2 points. I would define CO as the outer radius, which we could also use R if we wished. And I'm going to define this as rho y, the point of yielding, the radius of yielding. Anything beyond this distance from the center is going to be in full yielding. Okay, so again, rho y is the radius to the end of the elastic core, to the edge of the elastic core. So that is the gamma distribution. What about the tau distribution? What about the stress? We've looked at strain. What about stress? What about stress here? Now, while our strain is perfectly fine to increase as high as it wants, our stress can only go so high. In other words, notice on this graph, there is nothing restricting the strain. We're assuming the strain can go and increase right on up to infinity if it wants. However, our stress is limited. Our strain can go as high as it wants, but our stress cannot go any higher than our yield stress. So we're going to get this kind of distribution out of it. So I'm going to draw the same kind of system as before with a object with a circular cross section with a hole in the center. Another perfectly circular potato. I want to use the same color as I did last time. So I'm going to have, I think I'll actually make the hole green. I'll have a green hole in it, and then a blue elastic region, elastic core, elastic core here. That's a little too close. I don't think I like that. I want to have more room here. I'm trying to put it midway between. Even though it doesn't have to be midway between, the actual width of each of these bands is going to be entirely dependent on your loading, on your material, etc., etc. Okay. And so this is going to be our elastic core. Then we're going to have the hole in green in the middle. And then finally, in purple, I'm going to put my plastic annulus. And I'm going to plot my stress versus my strain. Or sorry, not stress versus strain, my stress versus the radius. All right, so what's going to happen here? Well, the stress is going to, actually let me label all these things just so you have it all on the same slide. This again is the plastic annulus. In blue, I'm going to have the elastic core. In green, I'm going to have the hole. And in black, I'm going to have the outer surface of the cross section. The cross section. Now, let's see here. So, very similar to the strain, the stress would start at 0 at the center. However, I have a hole here, so I'm not going to have to worry about that. It's not actually going to, it would go to 0 if this were solid, but because there's a hole here, it's simply going to start at that, the slope is going to increase as a line from the center, as in a linear relationship that would go to 0 at the center. So imagine projecting a line upward and then going maybe to this point here. I'm trying to draw this such that this stress here would be 0. This line would be 0 at the center. Okay, and this is going to be my tau, my stress, and this is going to be my radius. But then this line would pass through y equals 0 at the inner radius, or sorry, at the center. However, it doesn't actually reach that point because there's a hole there. Now, however, this thing is only going to increase to a certain point. Past that point, once it reaches the yield stress, it can't go any higher, so then it's simply horizontal, like this. So in other words, we linearly increase our stress from starting at 0 all the way to the yield stress, and then we just have a constant yield stress through the plastic annulus. So labeling some points. This again would be our rho yield. This would be our C outer. You know what, let me call this inner radius C inner here, just in case we need that. I'm going to call this inner radius here, that's CI if you can't read my crappy handwriting. All right, and then something to note is that throughout the cross section, or sorry, not throughout the cross section, throughout the plastic annulus in this entire outer ring, tau will equal tau yield. In other words, the shear stress is going to be equal to the yield stress. In the middle range, we will have this, in the middle ring here, we're going to have a linearly increasing, shear stress. But once we reach the shear stress, everything from that radius outward is simply going to be the yield stress. So clear as mud, right? So, in other words, what torque, to analyze this mathematically, we should ask, what torque to produce this tau distribution? Well, let's see. So I can say T total. Well, obviously, the total torque is just going to be the torque generated by the elastic portion plus the torque generated by the plastic portion. And then we can analyze these independently and see how these would work. So in other words, the total torque must be equal to all the torque generated by the elastic core plus all the torque resisted by the plastic core, or by the plastic annulus. So in other words, elastic plus plastic. So TE is going to be equal to tau yield, tau y, JE over rho y. Okay, let's see what this means. The torsion, the total torsion generated by the elastic core, is going to be the yield stress times the polar moment of inertia of just the elastic portion over the radius of the outer radius of the elastic region. And JE is going to be equal to pi over 2 times, let's see, this is going to be rho yield to the fourth minus C internal to the fourth. Okay, what this means is let me annotate this in some orange. Again, this is the elastic radius. And this is the internal radius, inner radius, if there is a hole. If there isn't a hole, then this is just going to be 0, and it's simply the polar moment of inertia of a circle with a radius of the elastic radius here. Now, so this stuff, these equations here, just the elastic portion is fairly easy. It just comes directly from our equations previously. But to actually develop the plastic will require something new. That's going to actually require a little bit of derivation. So let's look at that. So I need to derive the formula for plastic torque. Determine T plastic. How do we do that? Okay. So let us look at a system here with an annulus. I'm going to draw a couple arc lengths, and I'm going to have a little element of integration. Okay, so let us look at a piece of area, basically. I'm going to try to create a dA of an annulus and then basically integrate across the annulus. So we have our center here, and so we have a center. We're going to have the inner region of the annulus here, or the inner line of the inner arc of the annulus here, and the outer arc of our piece of the annulus here. Now, this is going to be a dA, so the difference between these radiuses is going to be very small. So I'm just going to say this whole thing has a radius of rho. It's just basic integration. Then I'm going to say this is going to be a d theta. And this is going to be dA. And this is going to be for from annulus, which will be equal to rho d theta D rho. And this, the difference between these inner and outer arcs, is going to be our D rho. So these are supposed to be circular, but I just can't draw. Okay, so D rho. And the arc length of this is going to be S times, or S is going to be equal to rho d theta. And so we can treat this as a rectangle, approximately. So the overall area of this dA is simply going to be rho d theta, the arc length, times the d rho. And that's the area of this. Okay. Now, from lesson 16, we know that TP, the plastic torsion, is going to be equal to the area integral of rho ta dA. This leads us to, we could think of this as the double integral. The plastic torque is equal to ta, which will be a constant, integrated from rho yield to the outer radius, integrated from 0 to 2 pi of rho squared d theta d rho. Just an area integral. And from this, we get that the plastic torque is equal to 2 pi over 3 times ta yield times C outer to the third minus the elastic radius also to the third. Or, so we now have the plastic portion. That is the formula for the torque of the plastic portion. And therefore, I can express the total torque for the entire system as, therefore, T total equals the elastic portion, which will simply be ta yield JE over rho y plus 2 pi ta yield over 3 times C outer to the third. Oh, that's god awful. Outer radius to the third minus the plastic radius, or the yield radius also to the third here. And that is our overall formula for the total torque in an elastic plastic member. Okay, so let me create a summary table for this, for our gammas. And then after that, I will finish up by working through a long-form example problem. Well, hopefully not too long, but just an example problem. So let me create a table, or a table as some people pronounce it, maybe somewhere. Table here. So I'm going to consider different states that we could be in. And look at the gamma therein. Okay, so we have different possibilities with this, and let's look at the 4 different possibilities. So we could have the elastic state, the max elastic state, we could have the partial plastic state, which is what we've really been working with so far, and we could have the fully plastic state. So the elastic is what we've been dealing with before in terms of previous lectures, where the yield radius is actually greater than the outer radius. In other words, we don't have any portion of the, actually let me do this in black. We don't have any portion of the cross-section in yielding. Everything is simply contained within the elastic stress region. So that's nice and friendly. Everything's just nice and simple, linear. We don't have to deal with any plastic problems. And gamma max is less than the yield strain. Max elastic, we have the yield radius exactly equal to the outer radius. And here, gamma max is going to be equal to gamma yield. So in other words, here we're taking the stress, we're taking the strain right up to the elastic strain on the outermost fiber, but no further. The partially plastic, this is the one that we've dealt with so far today. This is where the yield radius is less than the outer radius. So we have both a elastic and a plastic region. So gamma max is greater than gamma y. And then finally, we have a fully plastic. And what this means is that the yield radius is actually less than the internal radius. So what this means is that the gamma max is infinity. Interesting. So in other words, this is a fully plastic region. There is even all the way at the inner, all the way on the inner radius here, at the inner radius here, we have now exceeded the elastic stress, or reached the elastic stress. The stress would be flat all the way across the section. So this would mean that we could apply any. Gosh, I'm getting all tongue-tied. What this means is when the entire section is in a plastic condition, is that we have reached the limit. We cannot apply any more load. Even the slightest additional load results in infinite deformation. This is really when something's almost at the point of, or at the point of failing, when any more load equals an infinite shear strain. Okay. So let's see. I'm going to work through an example problem now. And for this problem, I'm going to have a solid 4-inch diameter circular shaft here. A 4-inch diameter circular shaft. And I'm also told that the yield stress is equal to 15 ksi. Oh, sorry, not the yield stress. The yield shear stress is equal to 15 ksi. And the yield strain is 0.001 radians, the gamma. And we, of course, because it's 4 inches, we know that the radius is 2 inches. So let's see. So let me do a quick drawing of this. This is a solid shaft, and it is under it's under a pure torsion condition with a torque on either end. So T here and a T here. And we are going to assume elastic plastic behavior for this thing as laid out here. So we are given this chart here that it linearly increases and then goes constant. And we are told that this is so this is going to be gamma and tau. And we are told that, so we're not given our G, but we can calculate it from what we've been given. And this is going to be 0.001 radians. And this is going to be 15 ksi. Okay, A. So I'm asked to calculate a few things. Basically, I'm asked to calculate the, actually, let me just list them out here. So all of this stuff is given, and then find A, max elastic torque. So in other words, what kind of torque can we take this thing up to? What kind of load T or torque T can we apply without putting any portion of the cross-section into plastic yielding? Torque if gamma max equals 0.002 radians. This will actually be a yield state. It will be in yielding here. So we're saying, okay, we don't care if it yields, but we don't want its angular strain to exceed 0.002 radians. And finally, what is the max torque period? In other words, find what is the maximum value we can ever take T, even if we don't care at all about just completely exceeding the yield stress throughout the section. So what is the maximum we can ever get out of this thing? So fully plastic torque. So let's run down the list and go through this. So A, max elastic torque. Maximum elastic torque. Well, here I'm going to say TE is equal to taw yield JE over rho Y equals 15 KSI times 4 pi inches to the fourth, so this is just plug and chug, 4 pi inches to the fourth over 2 inches. And this is going to be equal to 188.5 kip inches. And how I got JE, let me actually illustrate that. I'm kind of doing this backwards, but that's okay. JE, the elastic polar moment of inertia, is going to be pi over 2 times gamma yield, or sorry, rho yield to the fourth minus C internal, the internal radius to the fourth, is equal to, again, just plug and chug. So this would actually be our answer here, but I'm kind of doing this a little backwards just for fun. This would be equal to pi over 4 times 2 meters, or sorry, 2 inches. That's not 2 meters, not at all. To the fourth minus 0. And that's where the 4 pi inches to the fourth comes from. And so we have our maximum torsion, our elastic torsion, and now let me just plot the shear and the stress and the strain, the shear stress and shear strain for part A. Shear stress and shear strain plots, shear strain plots. So this is just going to be a nice simple plot. We don't deal with elastic cores or anything like that. And there's not even a hole in this thing. Everybody's happy. Everybody's good. So this one I'm going to have my stress, and this one my strain, both versus the radius or the distance from the center, rho. So rho and gamma, and rho and tau. Rho and tau. And then I'm going to have for both of these, the graphs are going to look very similar. Here I'm going to have rho yield, and here I'm going to have, well, that'll work. In other words, here my elastic radius is right at my outer surface here. And this is just a simple linear relationship with our elastic strain here, gamma y, linearly increasing from 0. And our strain is, and our stress is going to be very similar. It's just going to increase up to the point where we have the yield stress right on the outer surface of the circle. Tau yield like so. All right, for part B, what is torque if the maximum allowable strain is 0.002 radians. Now, I'll just tell you now, this is actually going to yield. To prove that, we could actually calculate this strain here, and we would find in the elastic region, and we would find that it is less than 0.002. So then we would know that if it's over 0.002, it must be yielding. Okay. So let's see here. Let me plot this here. I'll do the plots first this time. I'm going to have my rho and my gamma. We're not going to have a hole, but we're still going to have an elastic core here. And my rho and my my tau and my gamma, or my tau and my rho. Too many Greek letters this morning. Another perfect circle. All right, and I'm going to show the elastic cores in blue. Here. So I'm going to show the elastic cores in blue. This is the elastic core, and the same on the one on the right. All right, now this strain here. The strain is just going to linearly increase all the way to the outer surface. So the strain is just going to start at 0 and linearly increase all the way across the cross section as we get to higher and higher radiuses. So this here is going to be our C outer, obviously, and our yield radius will be somewhere in the middle. We know how to solve for that. But then the stress will not just simply linearly increase. The strain can go as high as it wants, but the stress can only go up to the limit, which is the yield stress. So we're going to linearly increase up until the yield stress, and then that's it. And this will be tau y, and then again, this will be at the yield radius. This is rho y here. All right, and then working through the formulas, let's actually find some of this. We need to actually find gamma y first. That's going to be the controlling factor, or it's not the controlling factor, but at least the first step. So gamma y over rho y is equal to gamma max over CO. In other words, it's just a simple relationship. It's a linear relationship. This is just a slope relationship. This is gamma max, which we were told was 0.002. So from this, we get the relationship. We can just plug and chug. That 0.001 radians over, and this would have been calculated based on, actually it wasn't calculated, this was given, this was the 0.0, we were told that the yield strain was 0.001 radians, over the yield radius, rho y, equals 0.002 radians over 2 inches. And from this, we get that rho y is equal to 1 inch. So the radius of the elastic region, of the elastic core, is 1 inch. Then, moving along, I can say I want to find the total torque. And the total torque, T total, is equal to T elastic plus T plastic is equal to tau yield JE over rho y plus the formula that we've developed previously for that we've seen previously for the plastic region, 2 pi over 3 tau yield times C outer to the third minus yield radius also to the third. Okay? And I need to find the JE first. Let me find the JE, the polar moment of inertia of the elastic region. is simply going to be pi over 2 times rho yield to the fourth minus C outer, C inner, not C outer. C inner to the fourth. However, this is going to be 0 because there is no internal radius. And this gives us, if you plug that in, you will get pi over 2 inches. And then finally, if we just do more plugging and chugging, T total will equal to 15 KSI times pi over 2 inches over rho yield, which is 1 inch, which we previously found, plus 2 pi over 3 times 15 KSI times 2 inches to the third minus 1 inch to the third. And all of this, if you enter that into a calculator, you will get 243.5 kip inches for the total torque of this elastic plastic condition. Now again, this is just one particular case of the elastic plastic condition. We could have a variety of them determined. We could have a variety of torque values just depending on what our allowed torsion was, or sorry, our allowed strain, our allowed angular strain was. But we can't get more than the elastic torque. This thing, basically, the torque here will vary between. It will start at the lower value of the partially plastic torque condition will be the lower bound of it will be the elastic, and the upper bound will be the fully plastic. So now let's actually find that fully plastic. Part C. C, fully plastic. Well, let me draw this really quickly. Now we're no longer going to have an elastic region. We are simply going to have, well, this is going to look a little funky. That's okay. We're going to have this rho and gamma, but this is just going to be a vertical line. This is just fully yielded all the way through. So gamma max equals infinity. It will twist as far as you want it to, because it is completely yielded. And then here, rho and tau, well, this is going to be constant. There's going to be a yield stress throughout the materials section. This is at the yield stress. So even at the center, even at the very center of the circle, it's going to be yielded. So here, to work with these equations, I can then say T fully plastic is basically equal just to the T plastic equals, it's the same formula as earlier, except I'm leaving out the T elastic because there's no more elastic region here. So 2 pi over 3 times tau yield times C outer to the third minus rho yield to the third. And this is equal to 2 pi over 3 times 15 KSI times 2 inches to the third minus 0. And if you plug this into a calculatron, I like calling them calculatrons. Sounds like it's from some, makes it sound like, makes a handheld calculator sound like some giant 1950s supercomputer. 251.3 kip inches. But that's neither here nor there. Now, back to sanity, what we can say is we can do a little bit of a check. And if we did this right, we should see that T elastic max is less than T partially plastic is less than T fully plastic. And let's check that. So 251.3 is indeed greater than 243.5, which is indeed greater than 188.5. So we're good. All of these have values in the ranges we would expect, and so that is how you handle torque conditions of both fully elastic, partially plastic, and fully plastic behavior. So hopefully that clears things up, or hopefully it doesn't just confuse you further. Read the book read section 5.9 in the Hibbler text for a more thorough explanation or further explanation. And we'll move shortly to the next portion of the lecture, which will be over section 5.5. All right, that'll do it, and thank you.